Hi, welcome to lecture 2A. This is our residential construction technology course, and we're going to be looking today at foundations. So this is lecture 2A. I'll break up lecture 2 into two components, so no one component is too crazy long for us. And it's based on chapter 6 of the Understanding Construction Drawings for Housing and Small Buildings, and chapter 7, which is Footings and Foundations for Canada Mortgage and Housing Corporation, the wood frame construction book that you downloaded. So we're going to be looking at footings, foundations, damp proofing, and waterproofing. Damp proofing and waterproofing in particular in 2B. So the areas of things that we're going to be looking at, we're going to look at the different materials and methodologies that are used for foundations in low-rise residential construction. We'll talk about some that cross over into larger projects like condominium projects, etc. So you should get a little bit comfortable looking at information, looking at a section detail, understanding what the components are so that you can visualize how they're actually going to be built and how everything goes together. And from that, you'd be able to look at dimensional requirements for foundation walls, thicknesses, some fundamental building code requirements as well, such as building on undisturbed soil. We're going to be using the National Building Code requirements, and that's in your CMHC book. It's also in the Understanding Construction for Drawings book. National Building Code, as you recall, that's the national standard for Canada. And Ontario Building Code takes from that standard, has its own unique requirements for Ontario, and goes from there. Although I will say I don't think there's any significant differences between Part 9 of the NBC and OBC when we start talking about footings and foundations. There's structural elements, and there's not massive changes from that respect for us. And so we'll look at also the aspect of damp proofing. What is damp proofing? What is waterproofing? When do we damp proof? When do we waterproof? And some of the differences that way. So I wanted to point out that in the Understanding Construction Drawings textbook, we're at the stage, so we looked at chapter 5, and we looked at the site and the layout and tried to visualize that process when we went through that one site plan and what that means for the topography of the ground, how that can affect the actual house. We talked about the permit process and understanding timing for permits and zoning and variances. So that was chapter 5, and the rest of the textbook really follows the flow of how we build a house. So if you're trying to think about how we build a house, we're going to be going chapter by chapter, which will kind of follow that rhythm with it. And in the book, we use a set of drawings called the Doncaster drawings. That'll help you visualize what the drawings look like. This course isn't being made, this particular course isn't being made just on drawings. It's really on the constructability and the technology of building in residential. But we have to be able to review drawings so we can actually build it. So chapter 6 will be looking at everything substructure, everything in the ground. We call that substructure because it's below the ground, so our foundations. And substructure is really kind of a ICI, institutional, commercial, kind of industrial term that you'll hear, because usually in residential everybody just says, oh, the foundation, footings and foundation wall, that kind of terminology. But really it is the substructure. Chapters 7, 8, and 9, we're going to be looking at framing. And so this is just a representation of a Gantt chart, but it's kind of showing you how things are constructed in a house and then what the chapters are actually referring to. So 7, 8, and 9, we're going to be looking at the structural elements of the house. That's part of the superstructure, what's above ground. So framing walls, framing floors, framing roofs. Chapter 10, we look at the exterior finishes, everything outside that separates the inside from the outside. So we're going to be looking at the roofing materials, we're going to be looking at the cladding, sidings, masonry work, And we'll also do a quick look at concrete slabs. Even though we have concrete slabs in the basement and inside the garage, we'll talk about it in Chapter 10. Chapter 11 is the building systems. So in Chapter 11, we look at all the systems, our plumbing, our electrical, our HVAC systems for the house, and how they are contracted and some of the things to consider and how these systems work and how they interact. We should be thinking of the house as a system because it is an integrated system. We have all these components, and you can almost think of it like the human body, right? Like if one part of the system is not well or it's dysfunctional, it causes problems in other areas. For example, if the roof leaks, it could be transmitting moisture through different areas of the house. That moisture could turn into mold. It could cause decay in the structure. It could cause some health issues and a number of other factors, just to name a few. So we like to think about buildings in general and building science as our buildings are part of systems, and it's a holistic system. So you can refer to it and conceptualize that. It'll be helpful. Chapter 12 is the envelope, and that's what separates inside from outside. So not only the cladding materials, but the insulation materials. We have air barriers, vapor barriers, weather barriers. We have this terminology that we have to get used to, and what does it mean and how does it work? And it really, if it's done wrong, causes a lot of moisture problems and potential issues in the house. So we spend a fair bit of time on Chapter 12, and of course with sustainability and upgrading of insulating values and building code requirements in the Ontario Building Code and the National Building Code. Chapter 12 is a very important area to look at and discuss. Chapter 13, now we're looking at everything interior. So as things progress, we're closing things in. Then we start putting the finishes on. So we want to make sure the house is all sealed up before we get to the stage where we're putting insulation in the walls in Chapter 12. And 13 is the finishes. And so now we're getting into things like finished stairs, drywall, finished floors, trim, doors, kitchens, cabinetry, millwork, all of these things. And so that sort of rounds out the process of building a house. We will be looking at Chapter 15 as well, but that's getting into more renovations and multi-unit buildings, like low-rise multi-unit buildings, townhouses, semi-detached, those kind of things. So that's kind of the flow of the course, and that's how this textbook will tie in very, very integrally to the flow of the course. And the CMHC book we'll use as a support that if you're unclear on things, you can always refer to the CMHC book for clarifications, and I will use periodically, as I did in this lecture, some of the slides to represent different views of the construction process. Okay, so we can get moving and get started on that part here. All right. And this is just, by the way, showing you a Gantt chart. Probably in one of the live sections, go through a Gantt chart and how that actually works. It's just showing a schedule for a house. This particular house is scheduled for around 140 days. Probably a more true, realistic view of the time frame in production building. If you're building a single house, it would typically take longer. So we start out with our footings, and really our footings provide the base for the whole house to sit on it. All of the loads imposed on the structure and the building, they rest on the footings, and those loads are distributed onto the ground. And so we have to make sure that the ground is able to carry that weight. And the types of loads that a building has, they're both live loads and dead loads. So a live load is something that moves. You invite your friends over and everybody's dancing on the deck in the backyard. That's a live load. It's movable, right? So it changes. You bring in furniture. That's a live load. You can move the furniture around. A dead load would be the drywall. It's screwed to the walls, the weight of the studs, the weight of the roof shingles, the weight of the concrete foundation walls, the weight of the studs. Something that is part of the building is a dead load. Live loads are also things like snow loads. So in the winter, when you get 2 feet of snow and then it rains on that snow. That's the composite snow load. It's very, very heavy. So our buildings have to be able to structurally take that weight. You could imagine if we had a big snowstorm and then it rained on it, and then if all the roofs started to collapse, that would be a catastrophe. So we have to build in factors of safety, and the Ontario Building Code and the National Building Code designates different areas by snow loads, just like we talked about when we were discussing drainage collection areas and floodplains, and the plan design so that the water will run off to storm sewers and be redistributed to the tributaries and streams and rivers that are close by. We have to think about things such as the snow loads and how it varies by community to community, town to town. So Thunder Bay would be different than Toronto. Collingwood would be different than Toronto. So we have tracked, basically government has tracked historically the amount of snow that falls in particular areas, and they designed the snow loads around 100-year worst storm cases. Plus they build in a factor of safety on top of that so that we don't have those types of situations occurring. Again, with climate change issues and things like that, we have to really be careful about what we're calling a 100-year storm. So some of these things are being reevaluated as we speak, pretty much. So live loads, dead loads, I think that's a pretty good definition of what we said. And they're all through the structure, right? And distributing weight onto the structure. This is a tack block detail. If you want in your own book to go through it, there's some extra ones too in chapter 4. So you could go back into the details section of chapter 4 and you can see these details pretty clearly. So tack block stands for Toronto Area Chief Building Official Committee. And so they put together a bunch of standard details, and this is pretty good for helping you to visualize what goes on in a foundation wall. So in a foundation wall, we have a footing. So the footing, you notice it's wider than the foundation wall. You have this little pipe at the side. We call that a drainage tile or a weeping tile. Very commonly called a weeping tile. We'll look at that later. We've got damp proofing on the wall. We'll talk about that. We've got a drainage layer that's on the outside. We'll show you some images of that later on. This is a symbol for styrofoam. So they put styrofoam on the inside wall, and then they built it in with a wood stud wall, and they've insulated that. Then they have air vapor barrier by the looks of it there, and they have drywall here. And so you can sort of see component by component. You can also see there's an anchor bolt, that little angle here with the dashed line. The dashed line represents something that is hidden, is an anchor bolt, and it attaches the sill plate to the foundation wall. Because it's Toronto Area Chief Building Officials Committee, they're not telling you the block size. They're not telling you whether it's going to be poured concrete or concrete blocks. They're saying it can be whatever you want it to be, but it must meet these design criteria, and they've taken this straight from the Ontario Building Code. So these sizes and dimensions, which we'll talk about, like minimum 200 millimeters from grade to siding, that's a building code requirement that says you're not to have the ground any closer than 8 inches, which is 200 millimeters. That keeps it in close proximity so you don't have what they call rising damp. So moisture doesn't rise up or snow get on your siding material and start to decay it. With brick, it's 150 millimeters, as you'll see. So this is for a foundation and a wall system that would use siding. It could use EIFS, exterior insulated finish systems, or stucco, as you would probably think of it. Those kind of materials. The other type that is very popular, particularly in the Greater Toronto area, not across the country. You go to Newfoundland, you don't see too many brick houses unless you're in downtown St. John's. Even then, most of them are wood siding. You go out west to Vancouver, they usually have composite mixes of different materials. Calgary's got its fair share of brick. It just depends where you're at. So there's some geographical preferences to where you are, but for sure the Greater Toronto area, and particularly Toronto, we like brick and we like stone, and it's very resilient in our kind of weather as well. So there, brick could be a little bit closer because it's a much more resilient material. although it can have problems as well. And we'll talk about that when we get to the exterior finishes portion, which I believe is chapter 10. So you can see though, and this is sloping, the grade needs to slope away from the house. We talked about that in the last lecture, how we try to get the moisture moving away, and we saw those different grading examples in the site plan. We've got gravel placed over here, so if moisture goes down, and it will, the gravel helps the moisture to seep through over the weeping tile, and the weeping tile will take excess water away from the foundation and redirect it towards the storm sewers. It'll connect up to the storm sewers. So we also have a concrete slab in the basement, and we got gravel below. So I would say it's worth your while to take a few minutes and go back to chapter 4, take a look at the details that are in chapter 4 to better comprehend what's going on piece by piece with these different elements. And also the nice thing about chapter 4, it's got a lot of reference material for different symbols, and this we'd call hatchings, so you can just look at something and get an idea what it is. Of course, here you could read what it is, so it's batt insulation, and that's foam insulation, so those are the symbols for that. And this is representing concrete or blocks, concrete blocks, depending on what you use. This is just showing a different detail, and in this case, this is for a heated crawl space. So if you don't have a full basement underneath, it would have a detail something like that, as opposed to an unheated crawl space, which tends to cause more problems. It's very hard to keep this section of the floor warm enough. We would, if you wanted to do it better than this, you would actually foam the underneath here, but your best solution typically is to do something like this, where you actually have a heated crawl space underneath from a building science point of view and from a moisture and condensation point of view. Both meet building code requirements though. So footings need to rest on undisturbed soil. So a footing needs to rest on undisturbed soil, and it must have a bearing capacity of 75 kilopascals. So what that means is footings have to be capable of sitting on the ground, and this is for part 9. This is all of this course, or most of this course, not all, but most of this course is based on part 9 of the building code. And part 9 is called Housing and Small Buildings. That's why the book you're using is called Understanding Construction Drawings for Housing and Small Buildings. Housing and Small Buildings is part 9. And part 9 refers to houses that are 3 stories or less in height, and will have a square footage that is less than 600 square meters. That's up just over, I think, 6,000 square feet. It's a very big house. Beyond that, you have to have it designed and engineered under part 3 of the building code to make sure that it complies with those standards. But in part 9, things are, because there's so many houses constructed and renovations done, it really sort of predefines a lot of what you can do. It doesn't preclude you from getting an architect or an architectural technologist. In fact, to get a set of drawings done and submitted for permit, they have to have what they call a BCIN number, a Building Code Identification Number, and they have to have, with that BCIN number, omissions insurance. And they would have had to written some tests to prove that they fully understand Part 9 of the Building Code. So, with this, you check the bearing capacity, it's capable, and undisturbed soil just means it hasn't been excavated before. If it's been excavated before and filled in, it's not compacted enough, it'll settle. It may be the soil capacity, the bearing capacity of the soil is not strong enough to support this structure. So for example, if you're building on like swampland, you got a lot of like peat, like topsoil decaying material, and it's spongy. You ever push your hands on topsoil? It's kind of spongy. That's not good for placing a foundation on. So the bearing capacity has to be suitable to carry that. So 75 kilopascals for buildings structured under Part 9 is what that requirement is. This has got nothing to do with like commercial buildings or that sort of thing, because they're carrying much, much larger loads, and they have to be engineered and designed under Part 3 of the Building Code. Also, when things have less than that bearing capacity, then you have to look at getting a design done. That may require excavating deeper. That may require putting reinforcing in the actual slab. That may require excavating out and putting in a engineered fill that is compacted to ensure it has the proper bearing capacity, and the footings and the foundation wall are reinforced with steel. So there's a number of factors that may preclude you just from designing under Part 9. But if everything is fine and it fits those requirements, then footing sizes, wall sizes, those can be extrapolated out of the building code. So the frost line is, for us, is 4 feet or 1.2 meters below grade. So we have to excavate at least 4 feet below grade. That is our requirements that we need to construct by. Because if we don't, frost in our areas and in Canada, if it's a heated foundation, we assume if it's a heated foundation that some of the heat will get out of the foundation, so it won't freeze around the base of the foundation. But we have to get at least below 4 feet. In some cases, the frost might go deeper than 4 feet in some places up north, and you go far enough, there's even areas where there's permafrost. Although with global climate change, those areas would be questionable in some cases. But definitely, we have to fit the requirements, and so 4 feet is our minimum. If you've ever seen a fence that was built and fence posts, and you look around the city and you see one's up and one's this and one's that, what happens is they weren't down 4 feet. They were maybe down 3 feet. And you have some cold winters and the frost goes down below 3 feet. It heaves the post up. Now you probably wouldn't notice what it heaves up in a year. It probably heaves it up 1/4 of an inch. And maybe in the spring it goes down 1/8. Some soil fills in underneath it, and so it doesn't go all the way down. Well, then the next year it goes up another 1/4 of an inch, and it goes back down 1/8. After about a dozen years, the fence might be 3 or 4 inches up or pushed off to the side because it didn't go down the full depth of the 4 feet. Somebody took a shortcut. Same thing would happen with a house or a building. Frost can move anything. So it would heave a foundation. People that, it's weekend warriors, as they say, go back and they add a room a porch onto the back of the house, and they don't go down 4 feet. After a number of years, you can see this in a lot of the old parts of Toronto with garages, with porches added on the back. They're all twisted and up and down and all over the place. They didn't go to undisturbed soil, and they didn't go down 4 feet, typically. This is engineered fill being put in for several sets of townhouses. This is up in Collingwood. They call it the shipyards. And so what they're doing here, this was a brownfield site. It's where they built the actual ships for much of the Great Lakes for over 100 years. And it's been highest and best use again that we talked about. Highest and best use says, well, this is abandoned. They couldn't make any money anymore building ships. About 25 years ago, so it's being repurposed. Fram is the builder, and they've been, over the last 10 years, remediating the soil, making sure that it's tested, and now this is very close to Georgian Bay. Georgian Bay is surrounding this whole area here, behind here, around the edge here, and so this has to be excavated. It has to be brought in compactable soil. In this case, looks like limestone screenings. And then it's being compacted. It'll be tested to ensure that it will be able to have the bearing capacity to carry the weight of the townhouses. This is straight from the National Building Code, pretty much the same thing in the Ontario Building Code. Minimum depth of foundation. So as we were saying, if you're on rock, you don't really have to worry about going down 4 feet, like the Canadian Shield. Everywhere is rock. Well, we don't have to blast out 4 feet of rock to put the foundation on more rock. In that case, then what usually is basically the Canadian Shield would be drilled. In those cases where the footings are going to go, it would be pegged, and then your footings would be formed to go along that and leveled out from that and stepped, I guess, with the rock, depending on the topography. in those cases. But typically this is where we're at, 1.2 meters. So this was my point with a porch in the back and frost, and how if it's not down 4 feet, this is kind of the scenario that I was mentioning. So here is footings that have been placed for individual residential houses. So these are for all single individual residential houses. And this area here would be where the garage goes. And this little sort of groove here is what they call the key. So I think if I go back a few slides, oh, it doesn't even show a key in that case. Okay, usually it shows a key, but one of the slides will show a key. So the key is to make the foundation wall sort of not want to slip or move from the key, so to better bond it to the footing. In ICI, they put a real piece of wood there, and it's got like a real formation, and it's really kind of a lock in place. In residential, they sometimes do a lot of shortcuts most of the time, any that I've ever seen. Somebody runs around either with a piece of wood or the edge of a shovel and just kind of puts a groove into it. Truth is, once you put the concrete slab on the inside and the earth on the outside, it's not going to move anywhere. So the footings are formed, they're pegged, they're formed so that they can be poured. There's that groove that I was mentioning about, the keying. And you can remember, I think we mentioned last lecture, the pegs are put into place to show where the forms have to be placed based on the site plan, which is showing the setbacks from the property lines of the site. Usually builders and something like this would get an Ontario landscape, an Ontario an OLS land surveyor to lay this out. So they would have all the pegs put in place, and then the forming crew would just from the pegs measure out, as I mentioned in the last class. So if this footing was 500 millimeters wide and the wall was 200 millimeters wide, and I knew where the peg was, then I can calculate where I need to put each edge of the formwork. And so everything is formed up, and then because you're, in this case, you're doing production homes. Remember I said 140 days? That's not a bad number for production, for probably around a 2,000 square foot house. You have production, you can do a whole bunch of footings all at once. If you're doing a custom home, it's going to take a lot longer than 140 days. A lot more difficult to line up the resources, the trades, and keep them there to do what they need to do. Production, you can get them, and you can get them, they finish one row, they go to the next, they go to the next. If I'm a subcontractor, I know how many plumbers I can keep on that site for the next 6 months. It makes it very easy to schedule the work. So in this case here, they've got a concrete pump and boom, and they're able to move and have the concrete pour out into the footings and then level it as it comes. And they're able to do this in a very efficient, productive manner. In low-rise residential, you might be able to pump it. You might have to wheelbarrow it in. It just depends. Renovations, very often you have to wheelbarrow things. Step footings are footings that are stepped, and so that they have different heights, and that allows for differences in grade. It also allows for if you're doing a renovation and the footings are at different heights, so that you can step down to the existing footing of the house, or ensure that the foundation is stepped to it so that it's got full bearing wherever it's going. So step foundations kind of look like, let's see, like this, steps. There's minimums and maximums that the building code has for the size of the steps. They don't want them too deep. I'd have to look that up right now to be sure, but I think it's 600 millimeters. So you can sort of see, this has a sloping grade, this particular house. Basement walkouts. You ever see a basement walkout? Because what's going to happen here, in this case, there's going to be a floor slab that's going to be going where my arrow is, and the grade is going to be much higher. So where the ground finishes will be 4 feet above where the bottom of this footing is. That will allow the basement walkout from that point. And then, of course, it's going to slope up and be filled in between the houses as it goes up the hill. So there's a lot of different materials that can be used for foundations, and different types that can be used for foundations. Economics usually determines what the the foundation type and choice criteria will be, regional preferences, weather conditions, etc. Availability of the skilled trades will be discussed too. And I won't go into too much detail because I know the book goes in pretty well into this, particularly the Understanding Construction Drawings text. So poured concrete is the most popular. Concrete block is next. Not as at one time it was the popular choice, but for the last 30 or 40 years, it's been poured concrete. You don't have the joints, less opportunities for leaks to occur. It is easy to do in a productive way because you just use the forms over and over again. So it gives a very good quality foundation and at a reasonable cost. And that's usually what you'll see. And so you use formwork to actually build it. There's many different formwork companies out there, and they have standard forms, and they just drop into place, pull them and pull them out. You use snap ties, and these ties tie the forms together, and then they snap off. So they're left in the concrete, and then they're patched to stop it from leaking. But they hold the forms at the exact spacing, whatever you're using. So if it's a 200 millimeter wall, approximately an 8-inch wall, about 7 7/8, then that would be the snap tie distance that the forms would tighten up against, so that would hold it at a consistent thickness. And then you need a lot of supports, so the formwork will have some sort of support criteria, and they'll have wedges to tighten up the forms to the snap ties placed all the way around. Different forming systems work different ways, as I mentioned. They kind of use a little bit smaller panel system than this now, because these panels were pretty heavy to move around. So there's always different innovations coming around with forming systems, but they pretty much all work on the same sort of criteria. Even in commercial work, they have some sort of snap tie system that holds them at the right spacing. And these components like the whaler and your horizontal bracing and ties to hold things in place, because concrete, when you're pouring it, there's a lot of what we call hydrostatic pressure. Like the concrete is very wet depending on the slump of the concrete, and it puts a lot of pressure on the formwork. So you have to be very careful that the formwork has been put into place and is structurally sound. Anchor bolts are put into the concrete as it is poured, so that those little L brackets that you saw in the section detail earlier, the dashed line, that's your anchor bolts. And that's what's going to tie the wood frame construction to the entire house. So that's really your poured concrete foundation. Now blockwork. Blockwork used to be very popular for foundations. This was a one-off infill house up near Avenue Road in Lawrence a few years ago. I don't see this very often. Maybe the builder was a masonry contractor, and that's what they do, so that's why they did it with concrete block. It's perfectly fine to do it building code wise with concrete block. It's more, in my mind, it's more work and it's more opportunities for leakage, but if it's done well, it won't leak. So what has to happen is a parge coat has to go on below grade. So you have to parge all the blocks to seal all the cracks. Usually that's about 1/4 to 3/8 of an inch thick. And the parge coat then will be later covered with a tar coating. You also have to put a curve at the bottom of the foundation, so any water will run towards where the weeping tile will be placed later on. They call it a cove. What's become kind of popular recently is insulated concrete forms. I would say they become a little bit more popular every year. They're kind of, if you like Lego blocks, they're like Lego blocks. And they pop together piece by piece, and they are the forms. So you brace them in place. Every company, ICF, Insulated Concrete Form Company, has their own system, and you follow their directions. You can take usually training. It might be like 3 days of training or something like that with that system. You become certified, and then you can install that system. I guess about 20 years ago, I did that for one of the forming systems, took the training. That was very interesting. The real skill is just making sure that you properly brace it, because it is very flexible. So you got to make sure whatever that manufacturer's requirements are, you follow it to the letter and then some. But then if you've got that, then it's great, because it is going to be a very solid wall. It's going to be a reinforced foundation wall. These separators hold the styrofoam at the proper spacing, and then these separators, you can screw drywall to them on the inside. You can even have ledges built into it to support brickwork like this has here. So the brickwork would go up above that. So you want to talk about a very well insulated wall that is totally soundproof other than the windows. It's a fantastic system. It's usually on the upper end of the market cost-wise. That's why you don't see it in production homes. You see it more in custom. You can do just the foundation or you can do the whole house. Preserved wood foundations, pressure treated wood. They're specially pressure treated. It's not just any pressure treated wood. It has to have a special stamp that I indicate in the book. And it's kind of more popular out west. I think here, if you said, oh, I'm going to buy a preserved wood foundation, people would look at you, what, wood below ground? But it has been around for 50 years or more, so it has proven itself. But I just think that there, you know, if you're building a house, there's probably this sort of resistance to purchasers. So you don't see, I've only seen like 3 or 4 of them in Ontario. I see them more out west, but I don't think it's a growing industry for those reasons. Easy to insulate, easy to finish in the basement. You have to have a sump pump in the basement and gravel base, and the water flows to that, and then you pump it away. But those are some of the aspects of preserved wood foundations. So they have a lot of good opportunities. I don't see any great thing. I think it's more just this perception issue that sometimes bothers people. So I think that's what I wanted to get sort of overviewed in part 1 of this lecture. And so now you got an idea of the different types of materials that are used. The aspect of that the foundation has to rest on undisturbed soil and has to have a bearing capacity of 75 kilopascals. If it doesn't, you have to have it engineered and checked and verified. Most municipalities want that anyways, and you are required to do that to ensure, because if you mess that up, the whole thing is toast, right? You've always heard, build on a good foundation, build on a good foundation. Don't build castles in the sand. Those are for reasons, right? Because that just means your whole house or building or structure is going to crumble and be very, 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 very expensive to fix. So we will leave that for lecture 1A, and we will return to finish off with lecture 1B. And make sure that you go through chapter 6 very thoroughly in the Understanding Construction Drawings, and then if you have a little bit of holes and voids, you can go through the CMHC book to connect the dots. Okay, so we'll be back with lecture 1B. I'm Tom Stephenson signing off, and have a wonderful day.